Right now, a frozen moon is hiding an ocean. Europa is smaller than our own moon, yet under its cracked ice sits more water than every sea on Earth combined, times 2. And in 2023, the James Webb telescope caught it leaking. Carbon, a building block of life, rising from a dark ocean no human has ever seen. We will travel across cracked ice, past killing radiation, down to a black sea that might be alive. If a hidden ocean pulls you in, subscribe and come along. Get ready. We begin. In 1979, a spacecraft named Voyager 2 swept past Jupiter and pointed its camera at a small, pale moon. The pictures came back, and the scientists leaned in close. Something looked wrong. Europa was smooth, almost too smooth. Every other rocky world they had seen wore scars. Our moon is covered in craters, thousands of them, punched in over billions of years by flying space rocks. Mars has them. Mercury looks like a golf ball that lost a fight. These holes are normal. Space is full of debris, and anything sitting out there long enough gets hit again and again. Europa barely had a mark on it. Picture a busy highway after a snowstorm. If the road is covered in tire tracks, you know cars have been driving for hours. If the snow is perfectly smooth, the storm just ended, or someone plowed it clean minutes ago. Europa's surface looked freshly plowed. That meant the surface was young. In space terms, young is strange. A moon that formed billions of years ago should be a punching bag by now, dented all over. For Europa to stay smooth, something had to keep erasing the damage. Something had to resurface the whole moon, wiping it clean like a fresh coat of paint. Scientists counted the craters they could find. On a world the size of Europa, they expected thousands. They found only a handful, a few sad little dents on a face that should have been ruined. So what does that? On Earth, we know the answer. Our planet hides its old craters because it is alive in a geological sense. Volcanoes pour out fresh rock. Oceans bury things in mud. Continents crawl and fold over millions of years. A living, moving world repaves itself. But Europa is tiny and frozen, sitting way out by Jupiter, where the sun is a faint dot. It should be a dead ball of ice, locked solid and motionless. Dead worlds keep their scars forever. The moon has held its craters for billions of years because nothing up there moves. Europa was breaking that rule. The smoothness was the first whisper of a secret. Whatever was smoothing the surface had to come from somewhere. Heat, maybe. Movement. Some hidden engine running deep inside a moon that looked like a frozen marble from a distance. Voyager could not see what that engine was. It flew past in a blur, snapped its photos, and kept going toward the outer planets. It left scientists with a question that would haunt them for decades. Why is a frozen moon acting like a living one? The images sat in files and textbooks. People studied that smooth, pale face and felt the pull of it. A world that should be still was clearly doing something, and the only forces strong enough to repave an entire moon are big, slow, and powerful. The kind of forces that need a lot of energy. There was a deeper hint too, almost hidden in those early photos. Across that smooth ice ran thin, dark lines, faint at first, like cracks in a frozen pond. The scientists squinted at them and wondered what could crack a moon. The answer was waiting under the ice. And the closer they looked at those cracks, the stranger Europa became. Those thin, dark lines turned out to be the strangest part of Europa. When the Galileo spacecraft arrived in the 1990s and looked closer, the faint scratches became something jaw-dropping. They were cracks, huge ones. They wrapped around the entire moon, crossing over each other in a tangled web, stretching for thousands of miles. Some ran longer than the distance from New York to Los Angeles, a single crack reaching most of the way across a whole world. And they had a color. Most of Europa is blinding white, brighter than fresh snow, because clean ice reflects sunlight like a mirror. But the cracks were stained, rusty, red, and dirty brown. They bled across the white like someone had dragged a muddy finger over a clean sheet. Up close, The moon looked cracked, scratched, and smeared, almost like the shell of an egg that took a beating. Something was leaking out of those cracks. The question was, what? The lines told a story of force. Ice does not crack on its own for no reason. To split a frozen crust thousands of miles long, you need a planet-sized push, something pulling and tearing at the whole moon over and over. The cracks were a map of that struggle, drawn right on the surface. Some of the lines came in pairs, with a stripe of dark material running down the middle. They looked like wounds that had opened, oozed, and frozen shut again, then opened once more in the same spot, over and over, like a scab that keeps getting picked. That pattern meant the cracks were active. The ice was splitting, leaking, and healing in a slow, endless cycle. So what was the rusty stain? Scientists ran tests on the color, comparing it to chemicals they knew. The leading idea pointed to salt. Salt from below, pushed up through the cracks, then blasted by radiation until it darkened into that reddish brown. If that was true, it meant the moon was pulling material up from somewhere deep and spreading it across the surface. Up from where, though? You can crack solid ice. You cannot make it bleed colored stains and refreeze in neat stripes unless something soft and wet is moving underneath. Dry, dead ice just sits there. The cracks were behaving like cuts in skin, and skin only bleeds when there is something flowing below it. Imagine a frozen lake in winter. The top is hard ice you can walk on. But if water still moves beneath that ice, cracks open, water seeps up, and the surface keeps shifting. A truly frozen lake, solid all the way down, stays quiet and still. Europa's surface was anything but quiet. The cracks were practically shouting a clue. Below the hard shell, something was wet. Something was moving. Something kept squeezing the moon hard enough to tear its crust open across thousands of miles, again and again, for ages. The smooth face had whispered the secret. The bleeding cracks said it louder, but to find out what was really down there, scientists needed to know one number. How thick was the ice? A few feet, like a winter pond, or miles of frozen rock standing between us and whatever moved below? The answer would split scientists into arguing camps for years. Here is the problem with Europa's ice. We cannot see through it. From space, all we get is the top, the surface, the white shell with its rusty cracks. What sits below stays hidden, locked behind a wall of frozen water. And the single biggest argument about Europa comes down to one question. How tall is that wall? The guesses are wild. Some scientists think the ice is only about 3 miles thick. Others think it could reach 25 miles or more. That gap is enormous. 3 miles of ice is one kind of world. 25 miles is a completely different one. Why does it matter so much? Because the thickness decides everything. If the ice is thin, say a few miles, then the ocean below sits close to the surface. Cracks could reach all the way down. Water could rise up, freeze, and carry secrets from the deep right to the top where our telescopes can spot them. A thin shell is a leaky shell. It connects the hidden ocean to the outside world. If the ice is thick, 25 miles of solid frozen rock, then the ocean is sealed away like a vault, buried, cut off. Nothing from below could easily reach the surface, and nothing we send could easily drill down to it. 25 miles may not sound like much, but think about it this way. The deepest hole humans have ever drilled on Earth took about 20 years and reached only around 7.5 miles before the heat and pressure stopped us cold. Now imagine drilling more than 3 times deeper through solid ice, on a moon hundreds of millions of miles away, in radiation that would kill you. That vault would stay locked for a very long time. So which is it, thin or thick? The honest answer is that we still do not know for sure. Scientists read the clues like detectives. They study the cracks, they measure how the ice bends, they look at the chaos terrain, those jumbled fields of broken ice blocks, and try to figure out how deep the cracks must go to make them. Different clues point different ways. The shape of certain craters hints at thinner ice in some spots. The way the whole crust shifts hints at thicker ice in others. It may even be that Europa is both, thin in some places, thick in others, like a frozen lake that is solid near the shore and dangerously thin out in the middle. That last idea is the one that excites people most. A shell with thin patches means doorways, spots where the ocean and the surface can trade material, spots where a leaking secret could escape. For decades, this stayed a paper argument. Scientists drew diagrams, ran computer models, and debated at conferences, all without proof. They were guessing at the height of a wall they had never touched. But arguing about the ice was really arguing about something bigger. The ice was just the lid. What everyone truly wanted to know was what the lid was hiding. Was there really an ocean down there at all? Or were they all chasing a ghost, dreaming of water on a moon that was frozen solid to its core? The proof came from an invisible force, and it arrived from a direction nobody expected. The proof that there was an ocean came from magnets. In the late 1990s, the Galileo spacecraft made several close passes by Europa. It carried tools that could feel magnetic fields, the same invisible force that turns a compass needle and sticks a note to your fridge. Galileo was not hunting for an ocean when it flew by. It was just measuring the space around the moon. What it found did not add up. Jupiter has a monster magnetic field, the strongest of any planet in our solar system. It is so huge and so powerful that it wraps around all of Jupiter's moons. Europa sits right inside it, bathed in magnetic force every second of every day. As Galileo passed Europa, it noticed the moon was pushing back. Europa had its own magnetic signal, and that signal kept changing. It flipped and shifted in a strange rhythm, always reacting to Jupiter, like an echo answering a shout. That rhythm was the clue. A solid ball of rock and ice cannot make a signal like that. To create this kind of bouncing, shifting magnetic field, you need something special. You need a layer that conducts electricity, a layer that can carry a current and throw the magnetic force back. And on a cold moon, there is really only one thing that fits: salt water. Think about how this works. When you stir salt into water, the water can suddenly carry electricity. Pure ice cannot do that. Dry rock cannot do that. A deep, salty, liquid ocean can. As Jupiter's magnetic field swept over Europa, a hidden salty ocean would react, creating exactly the wobbling echo Galileo was picking up. The numbers fit a global ocean, a sea of salt water, wrapped around the entire moon, sloshing beneath the ice. Invisible from the surface, yet loud and clear to a spacecraft that knew how to listen. This was the moment Europa changed from a curiosity into a target. The smooth face, the bleeding cracks, the arguments about ice thickness, all of it suddenly made sense. There really was an ocean down there. Galileo had felt it without ever seeing a single drop. Sit with how wild that is. We confirmed a hidden ocean on a moon hundreds of millions of miles away by reading an invisible magnetic wobble from a passing robot. The water announced itself through pure physics. With no drill and no sample, the discovery lit a fire under everyone who studied Europa. If there was a real ocean, then there was a real chance. Liquid water is the first thing life needs. Find the water, and you have found a place worth searching. But a few questions still stung. How big was this ocean, really? A shallow puddle trapped under the ice? Or something deep and vast, the kind of sea that could hold worlds of possibility? Galileo gave a hint that stunned the scientists who ran the numbers. The ocean under that thin, pale crust was so large that comparing it to Earth almost broke the imagination. Because for all our pride in our blue planet and its mighty oceans, Europa was about to make Earth look dry. Europa is small. That is the part that makes the next fact so hard to believe. This moon is smaller than our own moon. If you set Europa next to Earth, it would look like a marble next to a basketball. You could line up about 4 Europas across the face of our planet and still have room to spare. By every measure of size, it is a little world, and yet its hidden ocean holds more than twice as much water as every ocean on Earth combined. Read that again, because it sounds impossible. Earth is a giant blue planet. Our oceans cover most of the surface and plunge miles deep. The Pacific alone is so wide you could fit every continent inside it. We think of Earth as the water world. Take all of it, every sea, every drop in the Atlantic and the Pacific and the Arctic, and Europa's buried ocean still beats it, twice over. How does a tiny moon hold so much water? The trick is in the shape. On Earth, our water spreads out in a thin film across the surface. The oceans look huge to us, but compared to the whole planet, they are a shallow coat of paint on a very large ball. Most of Earth is rock and metal, dry all the way down. Europa works differently, in the best way. Its ocean is a deep shell wrapped all the way around the moon, under the ice and over the rocky core. Scientists think this ocean could be 60 miles deep in places. Some estimates push past 90 miles. Stop and picture that. The deepest spot in Earth's ocean is a place called the Mariana Trench, and it reaches about 7 miles down. A drop into that trench would crush almost anything we built. Europa's ocean might be more than 10 times deeper than that. Everywhere, around the entire moon, an endless dark sea with no shore, no surface to swim to, no sky above the water, just ice for a ceiling and rock for a floor. That is more water than your brain wants to allow on a frozen marble hundreds of millions of miles from the sun. And here is the part that gives scientists chills. Water is the first ingredient life needs. On Earth, everywhere we find water, even in boiling vents, frozen lakes, and pitch-black caves, we find life clinging on. Water is the deal breaker. No water, no life as we know it. Europa has water in staggering amounts. A bigger ocean than the planet that gave birth to every living thing we have ever met. So the question stopped being about water. The water was there, confirmed, vast beyond reason. The question became something heavier. Could anything be living in it? But before anyone could dream about life, one fact threatened to drown the whole idea. Europa sits so far from the sun that it should be frozen solid. Every drop of that ocean turned to rock-hard ice. By all the rules of distance and cold, that sea has no business staying liquid. It should have frozen completely ages ago. Something out there is keeping a frozen moon warm, and the source of that heat is one of the strangest tricks in the solar system. Out where Europa lives, the sun is barely a sun at all. Jupiter sits about 5 times farther from the sun than Earth does. At that distance, sunlight arrives weak and thin. If you stood on Europa's surface and looked up, the sun would be a bright dot, sharp and small, throwing about 1/25th of the warmth it gives us here. It would light your way like a powerful flashlight in a huge dark room. It would not warm your skin. The surface of Europa proves the point. Up on that ice, temperatures plunge to around minus 260 degrees Fahrenheit. That is cold beyond anything on Earth. The lowest temperature ever recorded at the South Pole does not come close. On Europa's surface, the ice is so cold it behaves like solid rock. You could carve it, build with it, shatter it like stone. So by every rule we know, Europa should be frozen all the way through. A solid ball of ice and rock, dead and still, locked up tight for billions of years. That is what makes the ocean such a puzzle. The water is real. Galileo felt it. But the sun cannot be the thing keeping it liquid. The sun out there is far too weak to melt a backyard puddle, let alone an ocean deeper than 10 Mariana Trenches stacked end to end. So, something else is doing the job. Something is pumping heat into Europa from a source that has nothing to do with the sun. Think about your own body on a freezing day. If you stand still in the snow, you turn into a popsicle. But if you do jumping jacks, you warm up fast, even though the air around you is just as cold. Your moving muscles make their own heat. The warmth comes from the inside, from work, from motion. The frozen air never gave it to you. Europa is doing jumping jacks. In a way, the moon is being worked, squeezed, bent, flexed by an outside force so powerful that the friction inside Europa turns into heat, deep below the ice, far from any sunlight. That inner warmth is what keeps the ocean from freezing. It is a furnace with no flame, running on pure force. And the force doing the squeezing is the biggest bully in the neighborhood, Jupiter. This changes how we think about where life can exist. For a long time, people drew an invisible ring around the sun and called it the comfortable zone, the band where a planet sits at the right distance for liquid water. Too close, you cook. Too far, you freeze. Earth sits right in the cozy middle. Europa sits way outside that ring, deep in the cold. Yet Europa has an ocean anyway. It broke the rule. It found a way to stay warm without the sun's help, using a different power source entirely. And if a frozen moon can pull that off out here, then warm water might hide in countless places we wrote off as too cold and dead to matter. That single idea cracked the search for life wide open. But how exactly does Jupiter heat a moon from millions of miles away without ever touching it? The answer is a slow, grinding, invisible squeeze. And it has a name. Scientists call it tidal heating. And once you understand it, Europa stops looking peaceful at all. Jupiter does not touch Europa. It does not need to. It squeezes the moon with gravity alone. Jupiter is the giant of our solar system, a planet so massive that more than 1,000 Earths could fit inside it. Its gravity is a monster grip, reaching out across space and pulling on everything nearby. Europa orbits close, circling that giant once every 3.5 days, and every time it goes around, Jupiter grabs it. Here is the part that creates the heat. Europa's path around Jupiter is a slightly stretched oval rather than a perfect circle. So as the moon orbits, it drifts a little closer to Jupiter, then a little farther away, closer and farther, over and over. When Europa swings closer, Jupiter's gravity pulls harder, stretching the moon. When it drifts away, the pull eases and the moon relaxes. Closer, stretch, farther, relax, again and again, forever. Squeeze a rubber ball in your hand. Press it, let go, press it, let go, fast as you can for a minute. Now touch the rubber. It is warm. You did not light a fire or plug in anything. The bending and flexing alone made heat. That warmth came from the work of squeezing. Jupiter is doing that to an entire moon. The whole of Europa flexes with each orbit. The ice bends, the rock bends, the ocean shifts and sloshes. All that bending creates friction deep inside, and friction makes heat. The moon is literally warmed by being kneaded, like dough worked by giant invisible hands that never stop. This is tidal heating, and it is powerful enough to keep an ocean liquid in a place where the sun gave up long ago. Now, picture the scale of it. The bulges Jupiter raises on Europa can lift the surface up and down by many feet with each orbit. The solid ice rises and falls like a slow breath, again and again, day after day, for billions of years. That endless flexing is the engine. It is the source of the smooth, resurfaced face, the bleeding cracks, the warm, hidden sea. All of it traces back to one thing. Jupiter never lets go. We see the proof next door. Europa has a neighbor moon called Io, which orbits even closer to Jupiter. Io gets squeezed so hard that it has become the most volcanic world in the solar system, covered in erupting mountains that spew fountains of lava hundreds of miles into space. Same bully, same squeeze. Io just sits closer, so it gets cooked instead of warmed. Europa sits a step farther out. The squeeze is gentler there, gentle enough to warm an ocean instead of melting the whole moon into a fireball. It landed in a strange sweet spot, hot enough for liquid water, cool enough to keep it. That balance might be the most important accident in the search for life beyond Earth. A moon caught between fire and ice, warmed just right by the grip of a giant. But this raises a sneaky question. Why is Europa's orbit stretched into an oval in the first place? Left alone, gravity would smooth it into a tidy circle over time, and the squeezing would stop, the heat would fade, the ocean would freeze. Something keeps Europa's orbit stretched, something keeps the engine running, and it involves a hidden dance between three different moons, locked together in a pattern that has lasted for ages. The secret to Europa's heat is a dance between three moons. Jupiter has dozens of moons, but 4 of them are giants, big enough to see with a cheap pair of binoculars from your backyard. The 3 closest are Io, Europa, and Ganymede. They circle Jupiter at different speeds, like runners on a track with different lane sizes. And long ago, these 3 locked into a rhythm that has held ever since. The pattern is clean and strange. In the time it takes Ganymede to circle Jupiter 1 time, Europa circles twice, and Io circles 4 times. 1, 2, 4. Every loop, the timing lines up. The 3 moons keep meeting in the same spots, again and again, like dancers hitting the same marks every chorus of a song. Scientists call this a resonance. It means the moons are gravitationally tied together, tugging on each other in perfect time. Here is why it matters. Each time these moons line up, they pull on one another with their own gravity. The pulls are small. A single tug barely moves anything. But because the timing repeats so precisely, the little tugs stack up. They add together, the same nudge in the same direction, over and over for billions of years. Push a kid on a swing and you already know how this works. One shove does little, but shove at the exact right moment every single time, and the swing climbs higher and higher. Small pushes, perfectly timed, become a huge effect. That is the power of rhythm. The moons are pushing Europa's swing. Their repeated tugs keep yanking Europa's orbit out of a tidy circle and stretching it back into an oval. Left totally alone, Europa's path would relax into a smooth circle over time, and the squeezing from Jupiter would fade away. The ocean would slowly freeze. The engine would die. The 3-moon dance never lets that happen. Io and Ganymede keep tugging, keep stretching the orbit, keep the oval alive. And the stretched oval is exactly what lets Jupiter flex and squeeze Europa with every loop. The dance feeds the squeeze. The squeeze makes the heat. The heat keeps the ocean liquid. It is a chain of cause and effect, millions of years long, and every link has to hold. Break any one of them, and Europa goes cold. Sit with how delicate that is. The ocean that might hold life stays warm for a reason that has nothing to do with Europa itself. 2 other moons happen to circle Jupiter in a perfect one, 2, 4 beat. And that rhythm, set billions of years ago, is the only reason that sea stays wet today. Change the dance, and you freeze a world. This is the kind of thing that makes scientists stare at the ceiling at night. A living ocean, maybe full of strange creatures, kept alive by the orbital timing of moons that have no idea the others exist. The universe built a furnace out of nothing but gravity and rhythm. So now the picture is taking shape. A frozen shell on the outside, a vast, warm ocean underneath, an engine of heat fed by a cosmic dance. Europa is starting to look like a hidden machine, quietly running for ages, rather than a dead rock. But that machine leaves marks, and in one place on Europa's surface, the ice is shattered into a frozen wreck so violent it looks like a crime scene. In some places on Europa, the ice looks like it exploded and then froze in mid-chaos. Most of the moon is cracked but flat, a smooth, white plain scratched with lines. Then you reach certain regions, and the whole landscape falls apart. Giant blocks of ice sit tilted and scattered, some the size of cities, shoved against each other at crazy angles. A few are flipped over, some have drifted and spun. It looks like a frozen sea that was smashed by a hammer, then froze solid before the pieces could settle. Scientists gave these zones a fitting name, chaos terrain, and it is exactly what it sounds like. Pure disorder, carved into ice. If you flew over a chaos region, you would see jumbled slabs and rafts of frozen material, broken and refrozen, like the aftermath of an earthquake in a world made of glass. To understand why this matters, picture a lake in early spring. The winter ice on top starts to melt and crack. Big plates of ice break loose and float, bumping and tilting, drifting apart, then locking together again when the cold returns. Sailors call that pack ice. Europa's chaos terrain looks almost exactly like pack ice, frozen forever in the act of breaking up. But pack ice on Earth needs one key thing to form: liquid water underneath. The plates can only float and shift if there is something wet below to float on. So when scientists saw frozen pack ice on Europa, their hearts jumped. These blocks looked like they had floated, which meant that, at least for a while, there was liquid water right beneath them, close to the surface. The ocean, or a pocket of it, had come up to meet the ice. That is a huge deal. Remember the big argument about how thick the ice is? Chaos terrain hints at an answer. In these spots, the shell may be thin enough or warm enough for the ocean to push up and shatter the crust from below. Something had to do the shattering. The leading idea is heat rising from the deep, melting the underside of the ice until it cracked, floated, and broke into rafts. Warm water or warm slushy ice came up, did its damage, and then the surface froze over the wreckage and locked it in place. That makes chaos terrain a frozen photograph, a snapshot of a moment when the hidden ocean reached up and touched the surface. The blocks are still sitting there, tilted and scattered, recording an event that happened long ago. And it gets better. If the ocean really did come up here, then it may have carried things with it: salt, chemicals, maybe even clues about what is dissolved in that deep sea. The wreckage of chaos terrain could be the ocean's fingerprints, smeared across the surface for us to read. This is why scientists circled these regions on their maps and marked them as the most important places on the whole moon. If you want to learn what is in Europa's hidden ocean without drilling through miles of ice, you go to the spots where the ocean already did the drilling for you. One chaos region stood out above all the rest: a scarred, jumbled patch with a quiet name sitting in plain view, holding a secret that would not be cracked until a brand new telescope turned its eye on it. That patch is called Terra Regio, and it was about to become the most famous spot on Europa. Terra Regio looks like a wound on Europa's face. It is a region of chaos terrain, a patch where the ice is broken, jumbled, and scarred. On a map of the moon, it shows up as a rough, messy zone surrounded by smoother plains. From a distance, it might seem like just another beat-up stretch of frozen ground. For years, that is mostly how scientists saw it. One rough patch among many. But Terra Regio had been quietly hinting at something for a long time. Back when the Hubble Space Telescope studied Europa, it found something interesting in this exact spot: salt, ocean salt, the kind you would expect to find dissolved in a deep sea, sitting right there on the surface of Terra Regio. That was a flag. Salt on the surface meant the ocean below had likely pushed material up into this region at some point. So Terra Regio was already a suspect, a place where the inside of Europa seemed to be leaking out, a spot where the curtain between the hidden ocean and the watching universe had maybe slipped open. Think of the whole moon as a sealed letter. The ice is the envelope, hiding the message inside. Most of Europa keeps that envelope shut tight, but in Terra Regio, the seal looked broken. Something from inside had spilled out onto the front, where careful eyes could read it. That made this scarred patch the perfect place to point a powerful telescope. If you wanted to sample Europa's ocean without flying there, without drilling, without landing, you would aim at the one region where the ocean had already done the work and carried its secrets up to the light. For a while, though, the tools were not sharp enough to read the message. Hubble could spot the salt and raise an eyebrow, yet it could not see the finer details. It could tell scientists that Terra Regio was special. It could not tell them the full story of what had risen from below. The region sat there, scarred and waiting, holding its secret in plain sight. Everyone who studied Europa knew it mattered. They just needed a better eye. A telescope strong enough to break a frozen patch of ice down into the very chemicals it was made of, from hundreds of millions of miles away. That sounds like science fiction. Reading the exact ingredients of a specific scar on a distant moon, just by collecting its light. For most of human history, it would have been impossible. Then we built a telescope that could do exactly that. In 2021, the most powerful space telescope ever made launched into the sky. It was designed to see the faintest light in the universe, to study the air of faraway planets, to look back almost to the beginning of time. It could also turn its giant golden eye on something much closer to home, a small icy moon circling Jupiter, with a scarred patch called Tara Regio waiting to be read. When that telescope finally aimed at Europa, it needed only a few minutes of its precious time, pointed at one rough region of ice. And in those few minutes, it caught Europa's secret leaking into the open. Frozen onto the surface of Tara Regio sat a chemical that changes everything we thought about this moon. The telescope was the James Webb, and what it found was the building block of life itself. The James Webb Space Telescope was built to look at the edge of the universe. Instead, it changed how we see a moon in our own backyard. Webb is the largest, most powerful telescope humans have ever flown into space. Its main mirror is a giant golden hexagon, wider than a city bus is long, made of 18 pieces that fold and unfold like origami. It floats about 1 million miles from Earth, far past the moon, sitting in the cold and the dark so it can catch the faintest light without anything getting in the way. This machine was designed to study galaxies so distant their light took billions of years to reach us. It was meant to peer at planets circling other stars, sniffing out the gases in their air. People waited decades and spent billions of dollars to build it. When it finally launched in 2021 and unfolded perfectly in space, it opened a brand new window on everything. And one of the first things it did was turn toward Jupiter and look at Europa. Here is the trick that makes Webb so special. Along with taking pictures, it splits light apart. When light from an object hits Webb, the telescope can spread it out into its colors, like a raindrop turning sunlight into a rainbow. And hidden in those colors is a code. Every chemical leaves its own fingerprint in light. Carbon dioxide leaves one pattern, water leaves another. Salt, oxygen, all of them mark the light in their own special way. When Webb spreads out the light bouncing off a surface, scientists can read those fingerprints and figure out exactly what the surface is made of. They can name the chemicals on a world without ever touching it. So when Webb aimed at Europa, it gathered the sunlight bouncing off the ice and split it into a rainbow of clues. Then scientists studied the pattern, hunting for fingerprints. The most amazing part is how little time it took. These observations only needed a few minutes of the telescope's time. A few minutes, pointed at a small moon, after a journey of decades to build the machine. In that short blink, Webb did science that no tool in history could have done. The team focused on the scarred region everyone already suspected, Tara Regio, the chaos terrain where the ocean seemed to leak up. They collected its light. They split it apart. They looked at the fingerprints frozen into that patch of broken ice, and one fingerprint jumped out, strong and clear, right where the ocean salt had been found before. Carbon dioxide, frozen solid, sitting on the surface of Tara Regio. That might sound ordinary. You breathe out carbon dioxide every few seconds. There is plenty of it in the air around you. But finding it frozen onto a specific scar on a moon, hundreds of millions of miles away, was huge, because carbon is the single most important ingredient for life as we know it. Every living thing on Earth, from the biggest whale to the tiniest germ, is built on a frame of carbon. Webb had spotted the building block of life, sitting on Europa's surface, in the exact spot where the hidden ocean seemed to reach up. But finding carbon was only the start. A bigger question hit the scientists almost at once. Where did this carbon come from? And the answer would decide whether Europa was truly special or just another frozen rock. To understand why a little frozen carbon dioxide caused such a stir, you have to understand carbon itself. Carbon is the backbone of life. Every living thing you have ever seen is built around it. Your skin, your bones, your blood, the food you ate today, the trees outside, the bugs, the fish, the germs too small to see. Strip them all down to their basic parts, and you find the same element holding everything together: carbon. There is a reason life chose carbon. Carbon atoms are like the ultimate building blocks, able to link up with other atoms in more ways than almost any element in existence. One carbon atom can grab onto four others at once, forming chains, rings, and complex shapes. It can build long ladders and twisting spirals. It snaps together like the most flexible toy bricks ever made, able to create millions of different structures. That flexibility is what makes life possible. To build something as complicated as a living cell, you need a material that can form a huge variety of shapes and connections. Carbon does that better than anything. It is the master builder of the chemical world. So, when scientists search for places that might hold life, carbon is near the top of the shopping list. Find water, and you have the liquid life needs. Find carbon, and you have the building material. Together, they are two of the most important ingredients on the whole list. Until Webb looked, this was the missing piece for Europa. Scientists were fairly sure the moon had a vast ocean. They were fairly sure it had energy from tidal heating, but they had no proof that the right chemicals were down there. An ocean of pure water, with the right ingredients missing, would be a dead end. Wet, yet lifeless. A clean, empty pool. Carbon was the question mark hanging over the whole idea. Without it, Europa's ocean might be a beautiful, useless sea. With it, the ocean suddenly had what it needed to, maybe, just maybe, cook up something alive. Then Webb found carbon dioxide frozen onto Terra Regio. The question mark started to straighten into something else. Picture trying to build a house. You have found a perfect spot with plenty of fresh water nearby. Great start. But you cannot build a house out of water alone. You need bricks. You need lumber. You need real material to shape into walls and rooms. Carbon is the lumber of life, and Webb had just spotted a delivery of it, sitting right where the ocean seemed to reach the surface. That is why a few minutes of telescope time made headlines around the world. A frozen moon, far from the sun, in the cold, dark edge of Jupiter's kingdom, had both of the big ingredients: water in staggering amounts, and now carbon, the master builder, found on its surface. For the scientists who had spent their careers staring at Europa, this was the moment the dream got real. The pieces were lining up. The shopping list was filling in. But one giant catch remained, and it could ruin everything. Finding carbon on the surface is good, yet it only counts if that carbon came from the ocean below. If it fell from space, or formed up top from sunlight and radiation, it tells us almost nothing about the hidden sea. So scientists asked the question that mattered most. Where did this carbon really come from? Finding carbon on Europa was thrilling. Proving where it came from was the real challenge. The carbon dioxide sat frozen on the surface of Terra Regio, plain to see in Webb's data. But the surface is the easy part to reach, which means there were a few different ways that carbon could have gotten there. Scientists lined up three main suspects, like detectives at a crime scene, and worked to figure out which one was guilty. Suspect 1 was space rocks. The solar system is full of flying debris, and a lot of it carries carbon. Comets and asteroids are loaded with the stuff. Over billions of years, countless bits of space rock have slammed into Europa. Maybe they delivered the carbon, dumping it on the surface, like a truck spilling cargo. If that was the answer, then the carbon had nothing to do with the ocean at all. It would just be litter from space. Suspect 2 was radiation chemistry. Europa sits inside Jupiter's brutal radiation field, blasted by high-energy particles every second. That radiation can break chemicals apart and force them to recombine in new ways. It is possible that the carbon dioxide formed right on the surface, cooked up by radiation tearing through other materials in the ice. If that was the answer, the carbon was made up top, again with no link to the hidden sea. Suspect 3 was the ocean. The carbon could have come from deep inside Europa, dissolved in the hidden ocean, then carried up to the surface through the cracks and chaos of Terra Regio. If that was the answer, then everything changed. It would mean the ocean itself holds carbon. The building block of life would be down there in the water, riding up to the ice. 3 suspects. Only one could crack the case wide open. Here is why this mattered so much. 2 of the 3 answers were boring. If the carbon came from space rocks or surface radiation, then Europa's surface had carbon, sure, but the ocean might still be a clean, empty pool. The exciting part, the living part, the hidden sea full of ingredients, would stay unproven. Only the 3rd answer, the ocean, would mean something huge. It would be the first real evidence that Europa's ocean contains the chemicals life needs. A direct sample of the deep, read from the safety of a telescope a million miles from Earth. So how do you tell 3 invisible suspects apart? You look for clues in the evidence, and the scientists had one powerful clue already in hand: location. Think about a detective dusting for fingerprints. The fingerprints alone are useful, but where you find them tells the real story. A fingerprint on the front door means one thing. A fingerprint on the locked safe inside means something far more serious. The carbon dioxide on Europa was spread unevenly across the moon. It was concentrated, piled up heavily in one specific place, and that place was the key to the entire mystery. If space rocks delivered the carbon, you would expect to find it scattered all over, since rocks hit the moon everywhere. If radiation made it, you might expect it across wide stretches of surface that catch the same blast. An even spread would point away from the ocean. A tight, concentrated patch, sitting in exactly one telling spot, would point straight down into the deep. So the scientists checked the map. They looked at where the carbon was piled highest, and the location pointed at an answer that sent a chill through everyone studying this moon. The carbon was piled up in Terra Regio, and that one fact pointed straight at the ocean. Remember what Terra Regio is. It is chaos terrain, a scarred patch where the ice is broken and jumbled, where the surface looks like it floated and shattered. It is one of the spots where scientists believe the hidden ocean has pushed up and touched the surface. The exact place where Hubble had already found ocean salt years before. Now, Webb found the carbon dioxide concentrated in that same region, heavily piled up right there in the young, broken, resurfaced ice, instead of being spread evenly across the whole moon. That location was the smoking gun. Walk through the logic the way the scientists did. If space rocks had delivered the carbon, it would be scattered all over Europa, since meteorites strike the entire moon at random. It would have little reason to bunch up neatly in one chaos region. If radiation had made the carbon, it would tend to appear across the broad areas that take the same blast from Jupiter, again with no reason to pile up in Terra Regio specifically. The only suspect that explains a tight pile of carbon in one resurfaced patch is the ocean. The carbon clusters in Terra Regio because that is where material from the deep rises up. The ocean carried the carbon to the surface and left it there, concentrated in the one doorway where the inside of Europa reaches the outside. After studying the data, both science teams reached the same conclusion. The carbon most likely came from inside Europa, from the hidden ocean itself. It was made down in the deep, then ferried up to the ice. That was the moment everything tilted. For the first time, scientists had real evidence about the chemistry of Europa's ocean without ever drilling through a single foot of ice. Webb had read the contents of a sea no human has ever seen by studying the chemicals it left behind on the surface. The ocean had reached up, and we caught what it was carrying. And what it was carrying was carbon, the building block of life, dissolved in a sea that holds more water than all of Earth. Stop and feel the weight of that. Somewhere under miles of ice, in total darkness, sits a vast ocean, and we now have proof that this ocean contains one of the key ingredients living things are made of. The water was already there. The energy from tidal heating was already there. Now the carbon was there too, down in the deep. This is why headlines exploded around the world. A frozen moon at the edge of Jupiter's kingdom had quietly checked off another box on the recipe for life. Each discovery had made Europa look more promising, and this one made it look downright thrilling. The scientists were careful with their words. They stopped short of claiming life. What they had found was that the ocean holds the right kind of chemistry, the kind that could possibly support living things. A promising place to look, rather than a place where life was proven. Still, the door had cracked open, and once you know an alien ocean holds water, energy, and carbon, your mind races to the obvious next question. But Webb was not finished with Tara Regio, because the carbon it found was a strange and special kind, the sort of carbon that, on Earth, life loves to build with. The carbon Webb found on Europa came in a complex form, and that small word, complex, carries enormous weight. When scientists first detect carbon dioxide, they often expect the simple version, plain carbon dioxide, the same gas you breathe out, frozen into ordinary ice. That alone would have been a fine discovery. But when the teams looked closely at Webb's data, they saw signs that the carbon on Tara Regio was more tangled and mixed than that. It came in a richer, messier form, bound up with other material in ways that simple surface ice would struggle to explain. Why does messy carbon matter more than clean carbon? Because life is messy. On Earth, living things are chemical chaos in the best possible way. A single cell is packed with thousands of different carbon-based molecules, all tangled together, reacting and combining in endless variety. Life runs on a wild, complex stew. The more kinds of carbon chemistry a place has, the more interesting it gets for anyone hunting for life. One of the lead scientists put the idea in plain terms. On Earth, life likes chemical variety. The more variety, the better. We are carbon-based creatures, and we thrive in a rich mix of chemistry. So a place with complex, varied carbon is a far more promising place to search than a place with just one clean, simple version. The complex carbon on Europa hinted at exactly that kind of richness. It suggested the ocean below held real chemical variety, the messy, mixed-up kind that life seems to love, rather than a plain bath of water with a little gas stirred in. Picture two kitchens. The first has a single ingredient on the shelf, just flour, nothing else. You could never cook a real meal there. The second kitchen is stocked with dozens of ingredients, spices, oils, all sorts of things to combine. Only the second kitchen can make something complex and delicious. Europa's ocean was starting to look like that second kitchen, stocked with a richer set of ingredients than anyone could prove before. Scientists stayed careful here too. Complex carbon is a promising sign, and it sits a long way from proof of life. Messy chemistry can form through ordinary reactions in water and ice, with nothing alive involved. Finding complex carbon shows the raw setup is richer and more interesting than a dead, simple world would be. It does not put creatures in the water. Still, the trend was impossible to ignore. Every time scientists looked closer at Europa, the news got better. First, a vast ocean, then energy to keep it warm, then carbon, the building block of life, and now complex carbon, the kind that hints at real chemical richness in the deep. Each discovery raised the stakes. Each one made the hidden sea feel more alive, more like a place where something could be quietly brewing. One more piece tied the whole story together, and it came from connecting two different telescopes across 2 different years. Webb had found carbon in Tara Regio, but Webb was not the first eye to flag this exact patch of ice as special. Years earlier, Hubble had spotted something else hiding in the very same spot, and when scientists laid the two discoveries on top of each other, the picture they formed was almost too clean to call a coincidence. Years before Webb, the Hubble Space Telescope had already stared at Tara Regio and found a clue: salt, ocean salt, sitting on the surface in that exact scarred patch. That detail mattered for a simple reason. Salt is what you find dissolved in a sea. Pour ocean water into a pan and boil it away, and you are left with salt crystals at the bottom. So salt sitting on the surface of Europa was a sign that ocean material had risen up and reached that spot. The deep sea had left its signature on the ice, right there in Tara Regio. For years, that salt was a strong hint on its own. It told scientists that Tara Regio was a doorway, a place where the inside of Europa connected to the outside, a spot worth watching. Then Webb came along and found carbon dioxide heavily concentrated in the very same region, in the exact patch where Hubble had spotted the ocean salt. Lay the two maps on top of each other, and the match is striking. Salt from the ocean, here. Carbon from the ocean, in the same here. Two different telescopes, years apart, using different methods, both pointing their evidence at one scarred patch of broken ice. When two clues line up that perfectly, scientists pay attention. One discovery in a spot could be luck. Two separate discoveries, both screaming the same answer in the same place, build a much stronger case. The salt said the ocean reaches this surface. The carbon said the same thing and added that the ocean carries the building block of life. Together, they told a clean story. Tara Regio is where Europa's hidden ocean breaks through to the top. Material from the deep rises through the cracked, chaotic ice and gets left behind on the surface. The salt is part of that delivery. The carbon is part of it too. Both came up from the same dark sea. This is huge, because it means we can study Europa's ocean from far away, just by watching the spots where it leaks. We can learn things long before we ever drill through miles of ice. The ocean is handing us samples, carrying its chemistry up to the surface in places like Tara Regio, where our telescopes can read it. Think of it like a sealed room with a secret inside. You cannot open the door, but there is a thin gap under it, and now and then, things slide out through that gap onto the floor where you stand. A grain of salt, a trace of carbon. Piece by piece, you learn what fills the room you have never entered. Tara Regio is that gap under the door. One scientist summed up the excitement. We may be able to learn basic things about the ocean's makeup even before we drill through the ice to get the full picture. That is the gift of these leaking patches. They are windows into a world we cannot yet visit. So now the case for Europa stood on solid ground. A vast ocean, confirmed by magnets. Heat to keep it warm, explained by tidal flexing. Carbon in the water, caught by Webb. Salt in the same spot, found by Hubble. Each piece supporting the next, building toward a picture that grows more thrilling with every new clue. Yet, one ingredient on the recipe for life was still missing. Water and carbon are not enough on their own. Life also needs a steady source of energy, deep down where the creatures would actually live. And the hunt for that energy leads to the strangest, darkest corner of Europa's hidden sea. Life needs three big things: liquid water, the right chemicals, and a steady source of energy. Europa now had two of them confirmed. The third was about to become the biggest question of all. Think of it like a campfire. You can have a perfect pile of dry wood and a clean fire pit, everything arranged just right. But without a spark, without a source of energy to get it going, nothing happens. The wood just sits there, cold. Life is the same. Water and carbon are the wood. Energy is the spark that brings it to life. So where would the energy come from? Deep in Europa's ocean. On Earth, most life runs on sunlight. Plants soak up the sun and turn it into food, and almost everything else eats the plants or eats the plant eaters. Sunlight sits at the bottom of the whole food chain. Pull out the sun, and most of life on Earth would collapse. But Europa's ocean gets no sunlight at all. None. It is buried under miles of solid ice, in permanent, total darkness. Even at high noon, the bottom of that sea is blacker than the deepest cave on Earth. No sunbeam has ever touched it. No plant could ever grow there. That sounds like a death sentence for life. For a long time, people assumed it was. A sunless ocean seemed like a frozen dead end, no matter how much water or carbon it held. Then, here on Earth, we found something that changed the whole story. Deep in our own oceans, miles below the surface, there are places where no light reaches either. The water is freezing, the pressure is crushing, and the darkness is absolute. By every old assumption, nothing should live down there. For most of human history, we thought the deep sea floor was an empty desert. We were spectacularly wrong. When explorers first sent submarines down to those depths, they found entire communities of living things thriving in the dark. Giant tube worms taller than a person, ghostly crabs, clams, and shrimp packed together in crowds. A whole bustling world, alive and busy, in a place with no sun at all. How? Because those creatures found a different spark. They feed on energy that comes straight out of the planet itself, from cracks in the seafloor where heat and chemicals pour up from below. Sunlight never enters the equation. That discovery flipped the search for alien life on its head. If life can thrive in the cold, black, crushing deep of Earth's ocean, feeding on the planet's own heat, then maybe sunlight was never required at all. Maybe an ocean buried under ice, far from any sun, could still find a spark of its own. And Europa, remember, has a powerful source of inner heat. Tidal flexing kneads the moon and warms it from within. If that heat reaches the bottom of the ocean, where the water meets the rocky core, it could create the very same kind of energy that feeds Earth's deep-sea creatures. That is the question that now drives the whole search. Does Europa's dark ocean have its own version of those life-giving cracks on the seafloor? Are there warm vents down there, pouring out heat and chemicals into the blackness? Because if the answer is yes, then Europa would have all three ingredients at once: water, carbon, and energy in the dark. The full recipe, sitting in a hidden sea. And to picture what that might look like, we have to dive into the strangest places on our own planet first. To understand what might live on Europa, you have to dive to the bottom of Earth's ocean first. Down there, miles below the waves, sit some of the strangest places on our planet. They are called hydrothermal vents, and they look like chimneys rising from the seafloor. Each one pumps out dark, scalding water loaded with chemicals from deep inside the earth. The water shooting out can be hotter than 400 degrees Fahrenheit. Hot enough to melt some metals, kept liquid only by the crushing pressure of the ocean above. These chimneys form where the planet's inner heat meets the sea. Cold ocean water seeps down into cracks in the rock, gets blasted by heat from below, then comes roaring back up, packed with minerals. As it hits the cold ocean, the minerals harden and pile up, building tall, dark towers. Scientists nicknamed them black smokers, because the cloudy water gushing out looks like smoke pouring from a chimney. Now, here is the part that matters for Europa. These vents are surrounded by life, crowds of it. Around the chimneys live giant tube worms that can grow taller than a grown adult, swaying in the dark with bright red tips. Ghostly white crabs scuttle across the rocks. Clams, shrimp, and strange pale fish gather in thick clusters. A whole crowded city of creatures, thriving in a place with no sunlight, freezing water, and bone-crushing pressure. It should be a desert. Instead, it is a zoo. How do they survive with no sun and no plants? The secret is, at the bottom of their food chain, down at the vents, tiny living things called microbes feed directly on the chemicals pouring out of the chimneys. They take energy straight from those chemicals and turn it into food, using the planet's heat instead of the sun's light. Scientists call this chemosynthesis, which simply means building food from chemicals. Those microbes feed the worms. The worms and clams feed the crabs and fish. An entire food chain, top to bottom, runs on the energy leaking out of the earth. The sun plays no part in it at all. This discovery rewired how scientists think about life. For ages, the rule seemed simple. Life needs sunlight. Find a dark, frozen, sealed-off place, and you find nothing alive. The vents shattered that rule. They proved life can grab energy from chemicals and heat, deep in the dark, far from any sunbeam. And that changes everything for a buried ocean on a distant moon. Look at the list. Earth's vent creatures need liquid water. Europa has an ocean. They need chemicals. Europa's ocean holds carbon and salt. They need heat rising from the rock. Europa has tidal heating warming it from within. Every box that lets life thrive at Earth's vents could, in theory, be checked on Europa too. That is why scientists get so excited about a frozen moon hundreds of millions of miles away. They have already seen this trick work. They have watched life flourish in conditions that look a lot like Europa's hidden sea, right here on our own planet. So the question sharpens to a fine point. Are there black smokers on the floor of Europa's ocean? Are there chimneys pouring heat and chemicals into that dark water, ready to feed a hidden food chain? To answer that, scientists had to figure out what sits at the very bottom of Europa's sea, and the floor down there turns out to be the most promising part of all. The bottom of Europa's ocean might be the most important real estate in the solar system. Here is why. Europa is built in layers, like an onion. On the outside sits the shell of ice. Below that lies the vast ocean of salty water, and beneath the ocean, at the very bottom, sits a core of solid rock. That rocky floor is where the magic could happen. Think about what that means. In Europa's ocean, the water sits directly against rock. The sea touches stone, and when water meets rock, chemistry comes alive. This matters more than it might sound. Imagine two containers of water. The first is a sealed glass jar, water touching nothing but smooth glass on every side. Nothing interesting happens in there. The water just sits, clean and empty, forever. The second container is a pot of water sitting on bare soil and rock, soaking up minerals, reacting with the stone, slowly filling with dissolved chemicals. Only the second one becomes a rich, living broth. Europa is the second container. Its ocean rests on rock, free to react with it, free to pull minerals and chemicals out of the stone. That contact is what turns a plain pool of water into a sea that could feed life. On Earth, this rock and water contact is exactly what powers the deep sea vents. Ocean water seeps into the rocky floor, reacts with the minerals, and comes back loaded with chemicals that microbes can eat. The rock is the fuel source. Without it, the vents would have nothing to give. Europa has that same setup waiting at the bottom of its sea. Miles of dark water pressing down on a floor of rock, with endless chances for the two to mix and react. There is even a chemical bonus hiding in this contact. When certain rocks react with water, the process can release hydrogen, a simple chemical that many microbes love to feed on. Scientists have studied this reaction closely, and they think Europa's rocky floor could be quietly producing hydrogen this way, with no volcanoes or sunlight needed at all. Free fuel, made by rock and water alone. This is a big deal because it solves part of the energy puzzle. Life needs a steady spark, and a rocky floor that pumps out hydrogen and other chemicals is a power source that could run for billions of years. Slow, quiet, and reliable. Stack this on top of everything else, and the picture grows almost dizzying. Europa has water, more than all of Earth. It has carbon, caught by Webb. It has heat from tidal flexing. And now it has a rocky floor where water and stone can mix into a chemical feast. Most moons in the solar system do not get this lucky. Many are frozen all the way through, or have oceans sealed off from any rock, sloshing between layers of ice with nothing to react against. Europa landed in a rare sweet spot, with liquid water pressed straight against stone. Scientists who study this call it one of the best setups for life anywhere beyond Earth. Every ingredient seems to be lining up in a place we once dismissed as a dead frozen ball. Of course, a rocky floor only matters if heat is actually rising through it, building those chimneys that feed life. The water and rock are in place. The real question is whether the furnace beneath them is burning hot enough to light a vent. So are there black smokers on the floor of Europa? Real chimneys, pouring heat and chemicals into the dark? This is the question that could decide whether anything lives down there. We know Europa makes heat. Tidal flexing needs the moon as it loops around Jupiter, warming it from the inside. That heat is the reason the ocean stays liquid in the first place. The real mystery is where exactly that heat ends up. Scientists picture two main possibilities, and the difference between them is everything. In the first version, Most of the tidal heat gets made inside the ice shell, up near the top. The flexing warms the ice. The ice keeps the ocean from freezing, and the warmth mainly comes from above. In this version, the rocky floor at the bottom stays fairly cool. Any vents down there would be weak and scarce, with little heat to power them. The ocean would be liquid, but the floor would be quiet. A calmer, empty sea. In the second version, the tidal heat gets made deep inside the rocky core. The stone itself flexes and warms, and that heat pours up into the ocean from below. In this version, the floor of Europa's sea would be hot and active, with strong vents pumping out scalding, chemical-rich water, black smokers, alien chimneys, exactly the kind of place that feeds entire crowds of life on Earth. The first version gives you a liquid ocean with a sleepy floor. The second gives you a roaring engine at the bottom of the sea, with everything life needs to thrive. Same moon, two very different worlds, and we cannot yet see which one is real. Why can we not just look? Because the vents, if they exist, sit at the very bottom of an ocean miles deep, under miles of solid ice, in a place no camera has ever reached. We can study the surface from afar. The floor stays hidden behind one of the thickest curtains in the solar system. Scientists do have reasons for hope. They study how the ice cracks and shifts. They look at the chaos terrain, those shattered patches where heat seems to rise from below. They run computer models of how the heat might flow. Several of these clues hint that real warmth reaches the lower layers, enough to keep things active down deep. There is another tantalizing sign. The same reactions between rock and water that could build vents would also pump out hydrogen and other chemicals, the very fuel that feeds microbes at Earth's vents. If Europa's floor is warm and active, it would be making both the heat and the food at the same time. The furnace and the feast together. Picture standing at the bottom of that ocean, if you somehow could. Total blackness above and below, crushing pressure on every side, and then, glowing faintly in the dark, a tall stone chimney pouring out shimmering hot water with strange pale shapes clustered around its base. That is the dream image driving this whole search. A living oasis in a hidden sea. We have not seen it. We may never see it from afar. To know for sure, we would have to go there and look. But heat from below is only one way to feed a hidden ocean. There is a second, stranger source of energy on Europa, and it comes from the most dangerous force in the entire neighborhood. The same radiation that would kill any visitor might also be feeding the sea. There is a second way to power life on Europa, and it comes from a surprising direction, from above, from the deadly radiation pouring down on the moon's surface. Here is how it could work. Europa sits inside Jupiter's enormous radiation field, blasted constantly by high-energy particles. When that radiation slams into the ice on the surface, it does something useful. It breaks water molecules apart. Water is made of hydrogen and oxygen joined together. When radiation rips into the surface ice, it can split those molecules, freeing the oxygen. So, the top of Europa, under that endless bombardment, becomes a place where fresh oxygen is constantly being made out of the ice itself. Oxygen is a powerful source of energy for life. On Earth, you breathe it every second to fuel your body. Many living things depend on it. If Europa is making oxygen up on its surface, that is a valuable resource, the kind that could help feed a hidden ecosystem. But there is a catch. The oxygen forms on the surface, way up at the top of the ice. The ocean, where life would live, sits miles below. For that oxygen to matter, it has to get down there somehow. It has to travel from the surface, through the thick ice, all the way to the water. So can it make the trip? This is where Europa's restless surface becomes a gift. Remember the chaos terrain, those shattered patches where the ice breaks, floats, and refreezes. Remember the cracks that open and seal over and over. Every time the surface churns like that, it can carry material down with it. Fresh oxygen made at the top could get folded into the ice and slowly dragged downward, like ingredients being mixed into dough, until it finally reaches the ocean below. Picture a conveyor belt running through the ice. Up top, Radiation cooks fresh oxygen out of the surface. Then the churning, cracking, refreezing crust slowly carries that oxygen down, deeper and deeper, until it spills into the dark sea. A steady delivery of fuel from the surface to the deep. If this works the way scientists suspect, Europa would have two separate power sources feeding its ocean at once. Heat and chemicals rising up from the rocky floor below, and oxygen sinking down from the irradiated surface above. Energy coming from both directions, top and bottom, meeting in the middle where life could use it. That double supply would be a remarkable setup. Most places that might hold life scrape by on a single thin source of energy. Europa could have two, working together, each one feeding the same hidden sea. This flips something dark into something hopeful. The radiation around Jupiter is brutal, strong enough to kill a person and fry a spacecraft. Yet that same deadly force might be quietly manufacturing the oxygen that helps keep an alien ocean alive. The danger and the gift come from the very same source. Scientists are careful to call this a strong possibility rather than a proven fact. We have good reasons to think the oxygen forms, and good reasons to think it can travel down. We have not yet measured it reaching the ocean. It remains one of the most promising ideas in the whole search. Still, every new clue keeps pointing the same way. Europa has water, carbon, heat, a rocky floor, and maybe oxygen too. The case keeps building. So scientists tried to catch the ocean in the act by hunting for giant geysers blasting into space. What they found, or rather did not find, became a mystery of its own. For years, scientists chased a thrilling possibility on Europa. Giant geysers, towering plumes of water blasting up from the surface and shooting into space. The idea was electric. If Europa's hidden ocean could erupt through cracks in the ice and fountain into space, then we would not need to drill at all. We could simply fly a spacecraft straight through one of those plumes, catch the spray, and taste the ocean directly. The sea would come to us, launched into the sky for us to sample. And there was real reason to hope. The Hubble Space Telescope reported hints of these plumes a few times, around 2013, 2016, and 2017. Each time, the data suggested water vapor rising high above Europa's surface, possibly geysers venting from the deep. Scientists were cautiously excited. It looked like the ocean might be spitting itself into space. But catching solid proof turned out to be maddeningly hard. The hints were faint and flickering. A possible plume one year, nothing the next. Scientists could never quite pin them down. The geysers, if they were real, seemed shy, appearing and vanishing like ghosts. So, when the James Webb Space Telescope turned toward Europa, hunting for carbon, one team also used the chance to look for these plumes. With the most powerful space telescope ever built, surely they could settle the question once and for all. Webb looked carefully, and it saw no geysers at all, no plume, no fountain of water rising into space, at least not while Webb was watching. That was a letdown for the scientists hoping to catch a sample the easy way. But the result was useful in its own quiet way, because Webb did not just shrug and walk away. It used the absence to set a firm limit, a ceiling on how much water Europa could possibly be venting. If huge geysers were erupting during those observations, Webb would have caught them. Since it saw nothing, scientists could say with confidence that no big plume was active right then. So what does it mean that Webb saw no geysers when Hubble had hinted at some? The leading idea is that the plumes come and go. They might erupt only now and then, at certain times, in certain spots, then fall silent for long stretches. Hubble may have caught rare flickers of activity. Webb may have looked during a quiet spell when nothing was venting. The geysers could be real and simply shy, hiding most of the time. One scientist put the honest version plainly. All they could say for certain was that they did not detect a plume at Europa during those particular observations. That does not prove the geysers never happen. It only proves none were erupting at that moment. This is the careful, real face of science. Sometimes the answer is a clear yes. Sometimes it is a clear no. And sometimes it is a maybe, a mystery left hanging, a question that needs a closer look to solve. The plumes stayed uncertain. The carbon, though, was rock solid. Webb had still caught the ocean's chemistry frozen on the surface, even without catching a geyser in the act. By now, Europa was looking more alive than ever. Yet for all its promise, this is a savage place to survive. The same world that might cradle life is wrapped in conditions that would destroy almost anything we know, and the first of those killers is invisible. For all its promise, Europa is one of the deadliest places in the solar system, and the first thing that would kill you there is something you could never see coming: radiation. Europa orbits deep inside Jupiter's magnetic field, and that field is a monster. It traps a storm of high-energy particles, whipping them around the planet at tremendous speed. These particles form belts of intense radiation, and Europa sits right inside one of the worst of them. The surface is constantly blasted, every second of every day, with no break and no shelter. How bad is it? Bad enough to kill a human in a matter of minutes. If an astronaut stood unprotected on Europa's surface, the radiation would tear through their body and deliver a deadly dose almost at once. There would be no time to explore, no time to plant a flag, barely time to look around. The surface is a death zone. This is hard to picture because radiation is invisible. You cannot see it, hear it, smell it, or feel it coming. There is no warning. You would stand on that bright ice, looking up at Jupiter filling the sky, feeling nothing at all, while invisible particles ripped through you and counted down your final minute. A silent, unseen killer covering an entire world. It is not only deadly to people, radiation wrecks machines too. It scrambles electronics, corrupts computer chips, and fries delicate instruments. This is a massive problem for any spacecraft we send. The same radiation that would kill an astronaut can destroy a robot's brain, leaving it blind and dead in space. Engineers know this all too well. When they design missions to Europa, radiation is the enemy they fear most. They have to wrap the spacecraft's most important parts in heavy shielding, building a kind of armored vault to protect the electronics inside. Without that armor, a spacecraft near Europa would not survive long enough to do its job. Now here is the strange twist that ties back to everything before. This deadly radiation is the very same force that might be making oxygen on Europa's surface, cooking it out of the ice to feed the hidden ocean. The thing that would kill a visitor in minutes could be helping to keep an alien sea alive. The same power, deadly above and useful below. There is one more mercy in all of this. The radiation pounds the surface, but it cannot reach the ocean. Miles of solid ice block it completely. Down in the deep sea, shielded by that thick frozen lid, the water stays calm and protected. Any life in Europa's ocean would be perfectly safe from the radiation storm raging far above its icy roof. That is almost poetic. The surface is a killing field, scorched by invisible particles. The ocean below is a shielded sanctuary, cut off from the danger by the very ice that hides it. The same thick crust that makes Europa so hard to explore is also what could keep its ocean safe enough for life. So the radiation cuts both ways. It guards the surface like a deadly fence, keeping visitors out and machines in danger. And it quietly protects whatever lives below by staying trapped above the ice. Radiation is only the first of Europa's killers, though. Even if you survived the surface and somehow dropped into the ocean, a second force would crush you long before you reached the bottom. Suppose you could survive the radiation. Suppose you dropped through a crack in the ice and into Europa's ocean. A second killer would be waiting, and this one would crush you. Pressure. Europa's ocean is staggeringly deep. Scientists think it could plunge 60 miles down, maybe even 90 in places. And above all that water sits miles of solid ice, pressing down on everything below. The deeper you go, the more weight piles on top of you, squeezing harder and harder with every mile. Pressure works like this. Every bit of water and ice stacked above a spot pushes down on it. Near the surface, there is little weight overhead, so the pressure is gentle. Go deeper, and the load grows. By the time you reach the bottom of a sea miles deep, the weight pressing in on you is almost beyond imagining. We know how brutal this gets, because we have felt it on Earth. The deepest spot in our ocean is a trench that reaches about 7 miles down. At the bottom, the pressure is so intense it would crush a person flat in an instant. It can implode a steel submarine like a soda can under a boot. Only a handful of specially built craft have ever survived a trip down there. Now, remember that Europa's ocean might be more than 10 times deeper than that trench. The pressure at its floor, where the warm vents and life would be, would dwarf anything in Earth's seas. A force so enormous it is hard to even put into words. Picture the heaviest weight you can imagine sitting on your chest. Now multiply it again and again, until the very idea of it makes your ribs ache. That is the world at the bottom of Europa's ocean, a place where the water itself presses in from every side with unthinkable force. This is why we cannot simply send a person to explore Europa's sea, even setting the radiation aside. No human body could survive that pressure. We would need machines built like tanks, designed to withstand a crushing grip far worse than anything our deepest ocean throws at our strongest submarines. Building such a machine, and getting it through miles of ice first, is a challenge beyond anything we have attempted. And yet, here is the twist that keeps hope alive. Crushing pressure does not stop life. On Earth, the creatures around the deep-sea vents live under enormous pressure and thrive anyway. Their bodies are built for it. To them, that weight is normal, the only world they have ever known. They are not crushed by it, they are made for it. So if anything lives at the bottom of Europa's ocean, it would be built for the crush too. It would feel right at home in a place that would flatten us instantly. The pressure that would kill a human might be nothing more than ordinary life to a creature born in that deep, dark sea. This is the lesson Europa keeps teaching. The things that seem most deadly to us, the radiation, the cold, the crushing depths, are simply the conditions of the place. Life, if it found a way to begin there, would have shaped itself to fit them perfectly. But there is one more feature of Europa's ocean stranger than the pressure, stranger than the cold. It is a quality so total, so absolute, that it would change the very nature of any creature living in that hidden sea. Europa's ocean exists in perfect, total darkness, and that single fact would shape any life within it more than almost anything else. Think about how complete this darkness is. The ocean sits under miles of solid ice, sealed off from the sky. No sunlight reaches it, none at all. Even on the brightest day, with Jupiter blazing overhead, not a single beam makes it through that thick frozen roof. The water below has never seen light in its entire history. It is blacker than the deepest cave, darker than a sealed room with no windows and no door. This is darkness on a scale we can barely imagine. On Earth, even the gloomiest places get a little light. A cave might catch a glow near its mouth. The deep sea fades to black slowly as you descend. But Europa's ocean is pitch black from top to bottom, edge to edge, all the time, forever. A whole sea wrapped in permanent night. So what would that do to life living there? On Earth, sight rules everything. Most animals rely on eyes to find food, dodge danger, and find each other. Light is so central to life here that we built our entire world around it. We wake with the sun and sleep when it sets. Our eyes are some of our most precious tools. In Europa's ocean, eyes would be close to useless. There would be nothing to see because there would be no light to see by. Any creatures down there would likely be blind, with no need for vision at all. Evolution does not waste effort building eyes in a world of total darkness. Why grow something to catch light that never comes? Picture what these creatures might be like instead. With no sight to depend on, they would explore their world through other senses. Maybe they would feel their way through the water, sensing tiny currents and vibrations on their skin. Maybe they would taste chemicals in the water to track down food, following faint trails toward the warm vents. Maybe they would sense heat itself, homing in on the glow of warmth from the seafloor. a whole way of living built around touch, taste, and temperature, with sight left out entirely. We see hints of this on Earth already. Creatures that live in dark caves often lose their eyes over generations, becoming pale and blind, navigating by feel and smell. Some deep-sea animals barely use vision at all. Europa would take that to the extreme, an entire ocean of life that evolved without ever knowing what light is. There is something haunting about that idea. A vast sea, full of strange creatures perhaps, all of them living and feeding and moving in absolute blackness, none of them ever aware that a universe of light exists above their icy ceiling. They would never see Jupiter, never see the stars, never see each other. Their whole reality would be touch and taste in the dark. It stretches the mind to picture a world so different from our own. A place where one of the things we treasure most, the gift of sight, would be pointless. Where life, if it exists, would be shaped by darkness into forms we can barely guess at. All of this raises the question that has been building this whole time. After everything, the water, the carbon, the heat, the darkness, could anything truly be alive down there? It is time to face that question honestly. So, could there really be life on Europa? After everything, it is time for an honest answer. And the honest answer is careful. First, the exciting part. Europa has an astonishing number of the things life needs. A vast ocean of liquid water, more than all of Earth. Carbon, the building block of living things, confirmed by Webb in the ocean's chemistry. Heat from tidal flexing to keep the sea warm. A rocky floor where water and stone can mix into a chemical feast. Maybe oxygen sinking down from above. Maybe warm vents rising from below. The list of ingredients is long, and it keeps growing. Now, the careful part. Having the ingredients for life is a very different thing from having life itself. Think of it like a kitchen stocked with everything you need to bake a cake. Flour, sugar, eggs, butter, all sitting on the counter. The ingredients being there does not mean a cake exists. Something still has to mix them in the right way, under the right conditions, for a cake to appear. Europa has the ingredients on the counter. Whether they ever got mixed into life is the question we cannot yet answer. And if life did begin there, scientists are realistic about what it would likely be. Not monsters. Not giant alien beasts swimming in the dark. The smart money is on microbes, living things so tiny you would need a microscope to spot them. Simple, single specks of life, the kind that dominated Earth for most of its history before anything bigger came along. Why microbes and not creatures? Because building complex life, the kind with bodies and limbs, usually takes a rich, steady supply of energy over a very long time. Europa's energy sources, while promising, may be thin and slow compared to the flood of sunlight that powers Earth's giant life. A dim, cold, sealed ocean might support tiny survivors. It would struggle to feed a whale. So the realistic dream is not a sea full of fish. It is a sea that might, just might, hold microscopic life clinging on around the vents, feeding on chemicals in the dark, the way Earth's simplest life forms do. Humble, tiny, and yet utterly world-changing if we found it. Because here is why even a single microbe would matter so much. As far as we know for certain, life exists in exactly one place in the entire universe, Earth. We have never found it anywhere else. If we discovered even the tiniest living speck in Europa's ocean, it would prove that life is not a one-time accident. It would prove that life can begin in more than one place, which would suggest it might begin almost anywhere the conditions are right. That would change how we see ourselves and the cosmos forever. A universe where life springs up on a frozen moon next door is a universe likely teeming with life among the countless other worlds out there. One microbe on Europa would hint at a living galaxy. So scientists hold both truths at once. Europa is the most promising place we know of to find life beyond Earth, and we have not found any. It is a door standing open, with the room beyond it still dark. Yet some scientists urge caution for a sharper reason. A recent study suggests Europa's hidden engine might be weaker than we hoped, and if they are right, the whole dream could be in trouble. Not everyone is convinced Europa is alive with possibility. In early 2026, a team of scientists raised a serious doubt that shook the hopeful picture. Their concern targeted the energy. Remember, life needs a steady power source, and one big hope for Europa was warm vents on the ocean floor, fed by heat from the moon flexing under Jupiter's pull. Those vents would need active cracks in the rock, places where water could flow into the stone, react with it, and carry chemicals back out to feed life. The new study looked closely at how hard Jupiter actually squeezes Europa today, and the results were sobering. The team found that the modern tidal stresses, the bending forces working on Europa right now, may be too weak to crack the rock deep down. Especially below the first 1,000 feet or so, the squeezing might simply be too gentle to keep fractures open in the stone. That is a problem. If the rock cannot crack, water cannot flow into it. And if water cannot flow into the rock, the chemical reactions that feed vents would slow or stop. The food source for life could dry up. The study pointed out another trouble. Even if Europa cracked more strongly in the distant past, those old fractures would not stay open forever. Over time, minerals can slowly fill the gaps, sealing the channels shut like cement filling a crack in a sidewall. Once the cracks clog, water stops circulating through the rock, and the deep contact that could feed life gets cut off. In short, this team argued that Europa's seafloor might be quieter than we hoped. The vents, if they ever existed, could be weak, sealed, or gone. And without active vents pumping out chemicals, one of the main ways life could survive down there would lose its power supply. This is how science actually works, and it is worth seeing clearly. For every exciting discovery, careful scientists push back, test the idea, and look for reasons it might be wrong. The carbon find was thrilling. The ingredients are real. But good science does not stop at the thrilling part. It keeps probing, keeps doubting, keeps asking hard questions until the truth comes clear. The doubters are not trying to kill the dream for fun. They are doing the essential work of testing it. If Europa's vents really are too weak to feed life, far better that we learn it now through careful study than that we fool ourselves with false hope. And the debate is far from settled. Other scientists still see strong signs of heat and activity in Europa's deep. The chaos terrain, the cracking surface, the resurfaced ice all suggest real energy moving through the moon. The question of how much heat reaches the ocean floor and whether it can power life remains wide open. Both sides have evidence. Neither has won. This is exactly why the dreaming has to give way to going. We have squeezed nearly everything we can out of telescopes peering from afar and spacecraft that flew past long ago. We have measured magnetic wobbles, read frozen carbon, mapped the cracks, and argued over the heat. To truly settle whether Europa could host life, we need to get close, really close. And that is no longer a distant fantasy. A spacecraft is already on its way, the largest of its kind NASA has ever built, racing across the solar system toward this very moon. On October 14, 2024, a giant rocket roared off a launch pad in Florida, carrying the most ambitious moon hunter NASA has ever built. Its name is Europa Clipper, and its entire purpose is to answer the questions this whole story has been asking. Europa Clipper is enormous. It is the largest spacecraft NASA has ever built for a mission to another planet. With its solar arrays spread out, it stretches more than 100 feet from tip to tip, longer than a basketball court. Picture a spacecraft so wide it would not fit inside a normal building, sailing silently through space toward a distant moon. That is the scale of this machine. It needs to be huge for a reason. Out by Jupiter, the sun is faint and weak, so Clipper needs gigantic solar wings to soak up every scrap of sunlight and turn it into power. Those massive arrays are what let it run its instruments so far from the sun, in the cold, dark edge of Jupiter's kingdom. Packed inside its body is a suite of 9 science instruments, each one designed to study Europa in a different way. Cameras to map the surface in sharp detail, tools to read the chemistry of the ice, radar that can peer down into the shell, hunting for water hidden below, instruments to measure the magnetic field and confirm the ocean's depth and saltiness, devices to sample the thin wisps of gas around the moon. Together, they form the most powerful set of eyes and senses ever aimed at Europa. The goal of all this is clear and bold. Europa Clipper will try to determine whether Jupiter's icy moon has the conditions that could support life. It will not search for aliens directly. It will not scoop up a creature or photograph a fish. Instead, it will measure whether Europa truly has what life needs: the water, the chemistry, the energy. It is checking whether the recipe is real, ingredient by ingredient, up close. This matters because everything we know about Europa so far has come from a distance. Telescopes peering from far away. The old Galileo spacecraft, which flew past decades ago with much weaker tools. We have built a strong case for Europa's ocean from these scraps, but we have never studied the moon with modern instruments, up close, again and again. Clipper will change that completely. Building this spacecraft took years of careful work and billions of dollars. Engineers handcrafted nearly every piece. They tested it against the brutal radiation it would face, shook it to mimic the violence of launch, and baked and froze it to match the extremes of space. Every part had to be perfect, because once it leaves Earth, there is no fixing it. It is on its own. And there is a human touch tucked aboard too. Clipper carries a poem and the names of more than 2 million people who signed up to send their names to Europa. A small piece of humanity, riding along on a journey to a place we may never personally reach. When that rocket lifted off in 2024, it marked a turning point. After decades of staring at Europa and wondering, we finally launched a machine built to go look. The dreaming phase was ending. The exploring phase had begun. But Jupiter is a long way off, and the path Clipper must travel to reach Europa is a strange, winding journey that bends across the solar system in a way you might not expect. Reaching Europa is not as simple as pointing a rocket at Jupiter and firing. The journey Clipper must take is long, winding, and surprisingly clever. Jupiter sits about 5 times farther from the Sun than Earth does. The total distance Clipper will travel to get there comes to roughly 1.8 billion miles. That number is almost impossible to feel. If you tried to drive it in a car at highway speed, never stopping, it would take you thousands of years. Clipper will cross it in about 5.5 years, arriving in 2030. Here is the surprising part. Clipper is not flying in a straight line to Jupiter. It is taking a winding detour that actually sends it the wrong way first. Why would a spacecraft head away from its target? Because of a brilliant trick called a gravity assist. The idea is to fly close to a planet and let that planet's gravity grab the spacecraft and fling it forward like a slingshot, adding speed for free. Done right, a spacecraft can steal a little momentum from a planet and use it to race ahead without burning extra fuel. Clipper uses this trick twice. First, in March of 2025, it flew past Mars, swinging close to the red planet and using its gravity to adjust course. Then, in December of 2026, it loops all the way back to fly past Earth, using our own planet's gravity to pick up another boost of speed. Mars first, then home again, each pass adding energy, before it finally arcs out toward Jupiter for good. It sounds backward, looping past Mars and returning to Earth when the goal is Jupiter. But this winding path is smarter than a straight shot. Carrying enough fuel to fly directly to Jupiter would make the spacecraft far too heavy to launch. By borrowing speed from planets along the way, Clipper gets the boost it needs without hauling mountains of fuel. The detour is the efficient route. Think of it like a skateboarder building speed at a skate park. Rather than pushing hard the whole way, they roll down one ramp to gather speed, use it to climb the next, and let the shape of the park carry them along. Clipper is doing the same thing with whole planets, riding their gravity from one to the next, gathering speed for the long climb out to Jupiter. After the Earth flyby, Clipper will swing far out into the solar system, arcing even beyond Jupiter's orbit before slowly falling back toward the giant planet. Then, in April of 2030, it will fire its engines and slip into orbit around Jupiter, finally arriving in the neighborhood it has chased for years. This long journey takes patience on a scale most of us are not used to. A child reading about Clipper today might be halfway through school by the time it reaches Jupiter. The scientists who launched it will wait more than 5 years just to begin the real work. Space exploration runs on this kind of patience, planting seeds now for discoveries that bloom years later. Every mile of that winding path has been calculated with incredible care, plotted long before launch, so that Clipper arrives at exactly the right place and time. It is one of the most precise journeys ever attempted, yet arriving at Jupiter is only the start of the hard part, because once Clipper reaches Europa, it faces the same deadly enemy that threatens everything in that region. And the way it plans to survive that enemy is the cleverest part of the whole mission. When Clipper reaches Jupiter, it will not orbit Europa, the very moon it came to study. Instead, it will orbit Jupiter itself, swinging out wide and only diving in for quick visits. This strange choice is the key to the entire mission, and it comes down to one deadly threat: radiation. Remember how brutal the radiation is around Europa. Jupiter's magnetic field traps a savage storm of particles, and Europa sits right inside one of the worst belts. That radiation kills people in minutes and destroys electronics fast. Any spacecraft that lingers there is in serious danger. So engineers faced a hard problem. To study Europa, Clipper has to get close. But getting close means soaking in deadly radiation that could fry the spacecraft's brain and end the mission early. How do you study a place that destroys your tools just for being there? Their answer is brilliant. Rather than parking Clipper in orbit around Europa, where it would bathe in radiation constantly, they put it in orbit around Jupiter on a wide, looping path. Most of the time, Clipper stays far out, in calmer space where the radiation is much weaker. Then, every so often, it dives in fast, swoops past Europa to grab its measurements, and races back out to safety before the radiation can do much harm. Picture someone who needs to grab something from a blazing hot oven. You would not climb inside and sit there. You would reach in quickly, snatch what you need, and pull your arm back out before you got burned. Clipper does exactly that with Europa. Quick dives in, fast retreats out, again and again. Dip and flee, dip and flee. This dive and retreat plan lets Clipper survive for years instead of months. Scientists figured this out early. A spacecraft parked right at Europa might last only a few months before the radiation killed it. A spacecraft orbiting Jupiter and only visiting Europa briefly could keep working for many years, gathering far more science before it wears out. Even with this clever orbit, Clipper still needs serious armor. The radiation during those close dives is still intense, so engineers built a special protective vault inside the spacecraft. The most delicate electronics, the brain, and the most sensitive instruments are tucked inside this thick-walled shelter, shielded from the worst of the particles. It is like a bunker at the heart of the machine, keeping the vital parts safe each time Clipper plunges into danger. The radiation was such a worry that it nearly delayed the whole mission. In 2024, engineers discovered that some of Clipper's parts might not handle the radiation as well as they had thought. For a tense stretch, the launch hung in doubt. Teams scrambled to test the components, studying whether they could survive the journey. After careful work, they found the parts would likely hold up well enough, and the mission stayed on track. This is the constant battle of exploring Jupiter's neighborhood. The radiation that makes Europa so deadly and so fascinating is the same force that makes it so hard to study. Every choice in the mission, the wide orbit, the quick dives, the armored vault, exists to outsmart that one relentless enemy. So Clipper will spend its years at Jupiter playing this careful game. Loop out wide, dive in fast, grab the data, retreat to safety, repeat. And each one of those daring dives is a flyby, a precious chance to study Europa up close. Over the mission, those flybys add up to something remarkable. Across its mission, Clipper will dive past Europa around 49 times. Each dive is a flyby, a quick, close pass where the spacecraft swoops in, scans the moon with all its instruments at once, and races back out. 49 chances to study a world we have only glimpsed from afar. The numbers behind these flybys are stunning. On its closest passes, Clipper will skim as low as 16 miles above Europa's surface. That is astonishingly close for a spacecraft traveling between worlds. From that height, its cameras and sensors can study the ice in incredible detail, spotting features far too small for any telescope back home to ever see. Why 49 separate flybys instead of just settling into one steady orbit? The wide looping path around Jupiter is the answer, and it brings a hidden bonus. Each time Clipper dives in, it passes over a different part of Europa. One flyby studies one region, the next swings over another, and another. After that, pass by pass, the spacecraft stitches together a map of nearly the entire moon, covering ground a single fixed orbit never could. Picture trying to study a basketball by only ever looking at one spot on it. You would learn that one patch well and stay blind to the rest. Now imagine slowly turning the ball, examining a fresh section each time until you have inspected the whole surface. That is what Clipper's many flybys achieve. Different angle, different region, every single pass, until almost the whole moon has been mapped. During each close dive, all 9 of Clipper's instruments work at once. As it streaks over the surface, the cameras photograph the ice, the radar probes for water hidden below, the chemistry tools read what the surface is made of, and the magnetic sensors measure the ocean's pull. Every flyby is a burst of furious activity, the whole spacecraft gathering as much as it can in the brief window before it must retreat from the radiation. Think about what these instruments could finally reveal. The radar could measure how thick the ice really is, settling the old argument between thin and thick shells. The chemistry tools could hunt for more carbon, for salts, for the building blocks of life across the whole moon, telling us whether Tara Regio was special or just one of many leaking spots. The magnetic readings could pin down the ocean's exact depth and saltiness. Piece by piece, flyby by flyby, the blurry picture of Europa could finally snap into focus. There is even a chance Clipper could solve the geyser mystery. If plumes of water really do erupt from Europa now and then, Clipper might catch one in the act during a close pass. It could fly through the spray and taste the ocean directly, sampling the hidden sea without ever drilling through the ice. The shy geysers that dodged our telescopes might finally be caught up close. Each flyby is also a gamble against the radiation. Every dive exposes Clipper to that deadly storm, wearing on its parts a little more each time. The mission is a race to gather as much science as possible before the radiation finally takes its toll. 49 dives, each one precious, each one pushing the spacecraft closer to its limit. By the end, we should know Europa better than we have ever known any ocean world beyond our own. And that knowledge points toward a future even bolder than a flyby. Because learning whether Europa could host life is only the first step. The real prize lies one giant leap beyond. Here is something important to understand about Clipper. Even with all its power, it will not tell us whether Europa has life. That part surprises people. After such an enormous mission, how can the answer to the biggest question stay out of reach? The reason is subtle but vital. Clipper is built to study habitability, which means whether Europa could support life. It will measure the water, the chemistry, the energy, checking whether the conditions for life are truly there. What it will not do is directly hunt for living creatures. It is checking whether the house is livable, rather than knocking on the door to see who is home. This is a key difference, and it is worth getting right. Imagine scientists announce that Clipper found Europa has perfect conditions for life. Water, carbon, energy, everything in place. That would be thrilling. It still would not mean we had found aliens. It would only mean we had found a place where life could survive. Whether anything actually lives there would remain a separate question, needing a separate mission to answer. So why send Clipper at all if it cannot find life directly? Because you have to know a place is livable before it makes sense to search it for life. Clipper is doing the essential groundwork. It will tell us if Europa is truly worth the enormous effort of a future mission to look for life itself. It narrows the search and shows us where to aim. Think of it like searching for a needle in a vast field. Before you crawl through the grass inch by inch, you would want to know which part of the field is even worth searching. Clipper scouts the field. It finds the most promising patch, the spot where the conditions are best, so a future mission knows exactly where to start digging. And that future mission is already being imagined. Scientists dream of a Europa lander, a spacecraft that would actually touch down on the ice, scoop up samples, and search them directly for signs of life. To land in the right place, that mission would need to know where to go. Clipper's maps and measurements could pick the landing site, guiding a lander to the most promising scar on the whole moon. Picture the chain of exploration unfolding. First, telescopes spotted the clues from afar. Then, Clipper arrives to study the moon up close, mapping it and confirming whether it is livable. Then, perhaps, a lander follows, touching the surface and searching for life in the ice. Each mission builds on the last, step by step, drawing us closer to the answer that has haunted this whole story. This is how the search for alien life truly works. Not one dramatic moment, but a long, patient chain of missions, each one answering a piece of the puzzle and setting up the next. Clipper is a crucial link in that chain, the step that turns Europa from a distant dream into a real, measured world ready for the next bold move. By the time Clipper finishes its work in the 2030s, we should finally know whether Europa is the promising ocean world we hope or a frozen disappointment. Either answer would be historic. A yes would point the way to a lander and a real search for life. A no would still teach us volumes about how ocean worlds work, and Europa is only one such world, because the most thrilling part of this entire story is what it suggests about everything else out there. Step back and look at what Europa really teaches us. A small, frozen moon, far from the sun, in a place we once wrote off as a dead ball of ice, turned out to hide a vast, warm ocean with the ingredients for life. And that changes how we see the entire universe. For most of history, the search for life beyond Earth focused on one thing: finding planets at just the right distance from a star, in that cozy band where sunlight keeps water liquid. Too close, and you cook. Too far, and you freeze. By that old rule, Europa should be dead. It sits far outside the comfortable zone, deep in the cold, where the sun is a faint and feeble dot. Europa broke that rule. It found a way to stay warm without the sun's help, using the squeeze of Jupiter's gravity to heat itself from within. Its ocean stays liquid in a place that should be frozen solid, and that single fact cracks the whole search wide open. Because if a frozen moon can hide a warm ocean, then the cozy zone around a star stops being the only place to look. Suddenly, countless cold, distant worlds become possible homes for water and maybe life. The universe gets far more interesting, with far more places worth searching than we ever dared to think. And Europa is not alone. Our own solar system holds other icy moons that may hide oceans of their own. Saturn has a small moon that shoots geysers of water into space, proof of a sea below its ice. Other moons of Jupiter and Saturn show hints of buried water too. We are starting to suspect that hidden oceans, sealed under ice and warmed from within, might be common across the cold outer reaches of space. Now stretch that thought beyond our solar system. There are billions upon billions of stars out there, and around them, countless moons and worlds. If hidden oceans are as common as Europa suggests, then the number of places where life could possibly begin is staggering. Not a handful of lucky planets in cozy zones, but a vast multitude of dark, warm seas scattered across the galaxy. This is what makes Europa so important and so unsettling. It is a single example that hints at a much bigger truth. One frozen moon, hiding a living possibility, suggests a universe that might be dotted with such places. Each one, a sealed dark sea where something could be quietly stirring. We do not yet know if anything lives in Europa's ocean. The carbon is real, the water is real, the energy is debated, the life is unknown. Clipper is on its way to bring us closer to an answer, and a lander may follow after. The story is still being written, and the most thrilling chapters lie ahead. But even now, Europa has already changed us. It has shown that the conditions for life can hide in the coldest, darkest, least likely corners. It has turned a frozen marble at the edge of Jupiter's kingdom into one of the most promising places we know, and it has whispered a question that will haunt humanity until we finally answer it. If life can begin on a frozen moon next door, hidden under ice and lit by no sun at all, then how alone are we, really, in a universe full of hidden seas? That is the secret Europa holds, and we are only just beginning to listen.